Yeah.
All right, so I can get, there we go. We left off kind of thinking about discrete random variables. So, I had this example where we've got some random variable, which was the number of hires this company has. I guess maybe it's a 20 example today with the fair going on. So we've got anywhere between 0 and 12. We then look at some historical data and kind of look at the frequencies of each one of those outcomes. Based off those frequencies, we can turn those into probabilities by simply dividing the frequency by the total number of observations or the total number of outcomes that we're looking at. So it's kind of very much like how we calculated relative frequencies. Shouldn't look a whole lot different. We said we can kind of do a nice visual. The visual shows us here, like, don't expect double-digit hires. The most common looks like is 3 and 4. And if I'm roughly trying to guess where the middle of this data is, I'm thinking it's probably around 5, 6, somewhere around there, right? Now, we see each one of these outcomes, and each one has a different probability of occurring, right? So we might be able to do something like find the mean of this discrete random variable. But what I simply want to add up every single possible outcome and then divide by the number of outcomes I have. So 0 plus 1 plus 2 plus 3 over 12, and divide by what? 13 different outcomes? Well, no, because some of them are more likely than others, right? So some of them should be influencing the mean more than others, which should sound very similar. Should sound like when we were calculating weighted means. Okay. So what did we say with weighted means? We were taking the sum of, if I can get this notation correct, right? We're going to go through every observation, multiply the value for x times whatever the weights we were using, add those all up, and then divide by the sum of our weights. Well, this actually becomes quite a bit easier because what are our weights now? Well, our weights are just how likely are these things to occur? Question, right? So we're thinking about, we're going to be using the probabilities, right, of every single possible outcome, multiply that by whatever the value of the outcome is. So the first one's not interesting, but 0 times 0, then go to the next outcome. 1, how likely is it to occur? Times 0.06. Then go to 2, how likely is it to occur? Times 0.03. Do that for every single observation, then add them all up, right? I then need to divide by the sum of my weights. So this kind of capital X is like the random variable, lowercase x is that it takes on a specific outcome, right? One of these values, right? So we can plug in different values for little x here and get into the probabilities, right? If I plug a 4 in, well, I know the probability I see a 4 would be 0.2. This is kind of my probability mass function. It's kind of not like a functional form yet, but that table tells me the probability of seeing different x values. So what's the sum of my probabilities going to be? I'm looking at, right? So kind of just remember 1 all the way to the very last possible outcome. But yeah, I add the probability up of every single outcome. This is 1. What can I essentially do? Just ignore the denominator, right? So really, when we have a discrete random variable, finding the mean is like a weighted mean, but it's easier because now we don't have to worry about dividing by the sum of the weights, right? The sum of those probabilities, the sum of our weights should always add up to 1. Okay. So it's actually like finding a weighted mean, right? But a little bit easier because that's sum of our weights, right? Or we write this in general like this probability mass function, right? Those should always be adding up to 1. Okay? So we're kind of just left with take every possible outcome you can see for this random variable x, multiply it by the probability that you see that value for x, and then add them all up. Okay? Any questions there before we keep moving? Shouldn't be too bad. So I kind of already mentioned this, like how would you do this in practice? We just go through every single possible outcome, multiply it by the probability that it occurs, and then add them all up. We don't have to add up the sum of the weights or add up the probabilities because we know those will always add up to 1. Here we can kind of see we get this mean of this discrete random variable to be just above 5. So if I think about kind of the range, if I was just looking for the middle point between 0 and 12, that would be what, 6. So why is it a little bit closer to 5? Well, because some of the outcomes that were lower were a little bit more likely than these outcomes that were a little bit higher. So those values are going to pull that mean down a little bit more, right? Because they're going to have a higher weight. Think about it, an extreme example, but an easy example too. So let's say, I think it might have been this before. So let's say, what do I want here? So here's the probability of seeing certain returns, right? And those two return values, maybe there's a 10% chance or probably a 0.1 that I see this return -10. Right? And then there's a 0.9% chance that I see, I don't know, let's do something I can do easy in my head here. That it returns 5%, positive 5. Right? So if I think about, I'm going to make this investment, I know that there's a 10% chance, sorry, probably a 0.1, 10% chance that I lose 10% in this investment, right? There's a -10% return. There's a 90% chance that I get a positive return. Now it's not as great, right? There's some potential for some loss here. Like once I actually make this investment, it goes one of two ways, right? I either lose, 10% or I'm going to make 5, right? And so what would be the expected value of this investment? Well, all I'm going to go through and do is, here's the X value that I'm interested in. Here's the probability I see these different X values. I would take the first one, -10 times 0.1 is -1. 0.9 times 5 is what? If I'm doing math in my head correct, 4.5. I'd add those two together, and I get that the expected return here will be 3.5%. Right? And the reason why is because it's way more likely that I see this 5%. Now in practice, I can't see 3.5, at least in the example I set up. I'm going to only see one of these two values, right? So it's a little bit weird because sometimes this mean of a discrete random variable isn't actually an outcome you can see. 5.14, I can't see that. The company's either going to hire 5 or 6 people this year, right? So the mean is just giving us an idea about where it's going to be. Once we run the experiment and see the actual outcome, it's going to be one of our, in this example, integer values, right? So we can occasionally get these examples where our mean isn't necessarily going to be discrete, right? But that's okay. It's still just trying to give us a measure of where the middle part of these outcomes are. I should say this data, but where the middle part of these outcomes are now. Does that make sense? Any questions on that? Now, I wouldn't want to just take the two outcomes and find the mean, not kind of like a weighted mean, because here, if I add these two up and divide by 2, right, just try to find the regular mean, this would be what, -5/2. I would think that this investment, that the mean is actually that I'm going to lose money. But remember, it's so much more likely that I get this smaller positive return that it outweighs that negative return, because that negative return is pretty unlikely for me to see, at least relatively, right? 0.1 versus 0.9. Any questions on that? So what do you think, hopefully you can see, like, when we're talking about like portfolio returns or investments, a lot of times you're coming up with expected values. You know that there's all these different possible return values you can see. Some of them are more likely than others. You can kind of come up with then what the expected value of that investment is going to be. That's a pretty practical use for what we're doing here. Now you could also look at the variance, right? So here you might think, this is important to know that I could see, I'm either going to lose 10% or gain 5. So even though that the mean is positive, it's kind of a risky investment, because there is still a 10% chance that I get a pretty big loss. And you could skew these numbers to be even different. So like maybe something like this, right? I think if you work this out, this would still be -1. And this is going to be like, what, 4.9 or something. You would still get, when you add these up, a positive return. But this is way riskier, right, than the other investment I had up there, because even though it's way less likely I see that -100, I mean, it's still possible I could see it. So the next measure we would want is, well, how risky this investment might be. We might want to calculate something like the variance, right? What is the variation that we see in these outcomes? Now, we don't want to kind of put too much weight on this value, because even though it varies quite a bit from our mean, right? It's what? 103.9 away from the mean. Pretty unlikely we're going to see that variation occur in the outcome. So we kind of go through the exact same thing what we were doing before with weighted variances. We'll take every outcome, subtract the mean, take that deviation from the mean, square it, And then we had one more step with the weighted mean, which was multiply by your weights. Here our weights are just the probabilities. So the probability you see that specific outcome, do that for every single outcome and then add them up. Once again, usually we would divide by the sum of the weights, but the sum of the weights here, our weights or probabilities, should always be 1. Okay. So this shouldn't be too bad. And just like always, we wanted the standard deviation. What do? You just take the square of the variance. All right. So nothing really new here. It's just kind of looking at it in a slightly different context than what we've done before. Okay. So if I had that example of the new hires, I now know that the mean was 5.14. I'll go to that first outcome of 0. I'll subtract that mean to 5.14, square that deviation. Once I do that, I'll then multiply by the probability I see that deviation. Notice here, well, if there's a 0% chance that I see the outcome of 0, when I multiply that deviation by that probability, it is 0. I add nothing to that mean. And then I go through every single other observation and then add one. So you can notice if I have a lot of outcomes, it could take a while to do by hand, right? But if I'm doing this in Excel, once I calculate the mean, I could like create another column where I just take this X value minus the mean, square it, multiply by the probability, then sum up that column. So we can kind of do this pretty quickly in Excel. Anything I ask you with an exam, I won't give you something like 12 outcomes. I'll keep it like small, like 4 or 5, right? But it's basically just a weighted variance, just like what we were doing before. Okay. Any questions over either of these? So I'm not going to use the iClickers today. I'm actually going to do an online quiz. I've got a couple questions for the next topic that we're going to talk about that I want to kind of have you work through, although I know that it might take a little bit of time. So I want you to kind of have enough time outside of class to work on those. But for these, we can kind of talk through them. All right. So hopefully you guys can maybe lead me to the correct answer. When we kind of talk about some of the principles. Right? So we said what now our weights are our probabilities. All right, and this is all we need to do to find the mean. Okay. So if I've got I don't know, some individual, they're going to get a certain bonus. I know they're either going to get 0, 3 million, 6 million, or $10 million, right? I'm trying to drop in the zeros here just to kind of keep it a little bit easier. And then there's different probabilities associated with seeing those different bonus amounts. So the most likely bonus this person is going to receive is 3 million. These are a little bit less likely, 0. That's all relative, right? But we kind of have varying probabilities. So if I'm just looking at this on its face, if I had to guess before I even plug these values in, around where should the mean of this discrete random variable be? Well, what value is going to influence that mean the most? Yeah, why? 3 million. Why? It's the most likely outcome. We're using our probabilities as weights. And so whatever has the highest weight will influence that mean the most. Well, our weights are probabilities, so whatever has the highest probability will influence that mean the most. So we know 3 will influence it quite a bit. Now there's 2 outcomes above 3, and they kind of have similar probabilities to this 1 and 0. So there's 2 outcomes above 3 million. They're going to pull the mean up a little bit more than this one value that's below 3 million, which was 0. So if I'm guessing here, I can probably rule out which 2 answers right away. A and B don't really make a lot of sense to me, right? Probably going to be that the mean is somewhere above 3. Probably not a whole lot of, further above 3. So 4.2, 4.7, those seem like reasonable answers, right? So I can probably rule out A and B right away. Let's say I also had up there something like 7.4. That probably seems a little bit too high, right? I mean, these are the 2 most likely outcomes. So if I'm guessing, it's probably somewhere between 3 and 6 million. The 10 and the 0 would be equally far away, and their probabilities are similar. So, it's hard to say, depending on what the probabilities and the values are, exactly what the range of like possible values would be. But I think, hopefully I'm giving you like a little bit of insight where you can rule some out, right? Here we could rule A and B out. And if we saw something as high as like 7 or 8, it's pretty unlikely that the mean's going to be that high, just looking at the values. But how would we actually compute this? All right, so what would be the process that I do here? If you were writing something down, what's the first number you'd write down here? What number? There's 8 to choose from. 10. Right, 10. Okay. Then what would you do? Multiply that by the probability you see 10 occur, or 0.15. Then what's the next step? Take the next possible outcome of 6, multiply by the probability that you see that 6 million occur. And then we've got 2 more, 3 million times the probability you see 3 million occur, and the outcome of 0 times the probability you see 0 occur. As simple as that. Okay. Any questions on this before we keep moving? I guess that should be kind of review. We've really done weighted means that were actually harder than this. But I think if we do this, oh yeah, okay, I have it up here. We get 4.2 million. You enter that into your calculator. Okay. So now we're going to go starting out with this 4.2 million. How would I calculate the variance? What's the, well, first of all, if I'm looking at these, what can I rule out right away? Negative makes no sense. The variance, no matter what context we're talking about, a regular variable, we're doing a weighted variance, we're doing a variance of a discrete random variable, variation at the very lowest is 0, right? So we know that it has to be at least 0 or above. And in fact, we know it can't be 0 because if it was 0, what would have to be true here? One of our probabilities would have to be no variation in the discrete random variable would mean that one of the outcomes would have a probability of 1. Right? It'd be guaranteed. That's the only value we can see. 0 variation in the outcome. Okay. We don't have that here. So we know it has to be above 0. Now, if I'm looking at the other 3, it's hard to kind of gauge exactly what the value of the variance is going to be. But I'm thinking about that mean of 4.2. I mean, I'm seeing values that are 5, 6 away from that, 4 away, right? So I'm thinking probably a variation as low as 1.8 doesn't make a lot of sense. But whatever that variation is, I am multiplying it by these decimal values, these probabilities. So it's kind of hard to do. So I probably can't rule anything else out there. If I was a betting man, I'd probably go with A or C. C seems a little bit improbable since it's the same value as the mean, but it's still possible, right? That just depends on what numbers I choose. I could have chosen numbers very carefully to have it work out that way, right? But if I'm kind of just guessing, a betting man here, I'm probably going with either A or C. D seems a little bit too low, just looking at the range of possible values, 0 to 10 there. So what's the first thing I'm going to do if I'm calculating this variance? What number am I going to write down? Maybe start with the same one that we did for the mean, so 10 million. I'll then subtract that mean that we found of 4.2. I'll square that deviation and then multiply that by the probability that I saw that outcome of 10 occur. And then going to go through, do that for every single, what is this, 0.25? Every single possible outcome. So I'll go to the next outcome of 6 million. I'll write this out, but shouldn't be too bad, right? I think this is, like I said, a little bit of a review. All right, if we do this, I believe you'll get 9.96. Okay. Any questions just kind of on the process? Like I said, it should look familiar, should look like things we've kind of done before. Okay with this? Good. All right. So before I move on to the next topic, does anybody recognize what these stills are from? I looked it up. What is it? Big Short. Yeah. So if you guys haven't watched this movie as business students, you definitely should. It's like a really entertaining, but it does a really good job of explaining what happened in the 2008, 2009 kind of recession with these mortgage-backed bonds and why it caused the economy to kind of crash like it did, right? And it does it in a very fun, easy to understand way. I just tell people and also you should be able to talk about that, like I said, as business students. It's not in the too distant past. It's a fun movie. I always tell people, my sister, I remember actually, this is one of the last, I don't usually go to the theaters, but I remember I saw this and our family was together. So we all went and she actually enjoyed it. She's like the most bohemian hippie person you can ever think of. Like she hates numbers, like talks about crystals, and she enjoyed this movie, right? So I think that, you guys will find some interest in it, at least being able to even understand better what they're actually talking about. So, all right, you'll never meet her, but hopefully she she doesn't look up these YouTube videos and hear me say that. So, but we're okay with that. We'll kind of jump to the next topic. The online quiz I posted, I have a couple questions related to this because it is kind of tough, and I'm going to have you work it out by hand on the exam. Now I'll show you how you can use Excel. The function Excel is a little bit tricky, actually. I think once I probably won't get this today, but probably on Friday when I show you a little bit more of how we do this in Excel, I'll kind of show you why sometimes doing it by hand can prevent you from making some mistakes, or at least knowing how to do it by hand will allow us to identify maybe how we incorrectly entered it into Excel, right? So the idea of a binomial distribution, right? Thinking about binomial, so bi meaning two outcomes, right? So we're going to run a certain number of experiments, right? So we got this discrete random variable, right? We're going to run this experiment a certain number of times. We don't know what the outcome is going to be. And we'll kind of call that number of times we run this experiment n. Now, every time we run this experiment, there's only two different outcomes we can see. And we'll say for now, success or failure, or like a binary. It's either a 1 or a 0. I either see what I'm interested in or I don't. Okay. So this would be like flipping a coin. I either see a heads or a tails. Right. If I choose somebody at random, they either have blue eyes or they don't. Right. So we're kind of thinking about almost like an event and its complement. Right. We can only see two outcomes occur. Okay. The probability of success we're going to need to be the same across every single trial. Okay. So if we had, flipping a coin, my probability of success in every trial is just going to be, what's the probability to get a heads on every coin flip? 0.5. It's a fair coin, right? Now, in kind of the eye color example, what I could do is, I know that the population as a whole has something like, I looked this up, I think it's like 15% people have blue eyes. So I know that if I'm selecting people at random every single time, there's a 15% chance they have blue eyes, or a probability on every single random person that I'm pulling out of the crowd of about 0.14, 0.15. So I've got this underlying probability of success that doesn't change, right? When I'm running this experiment over and over. And then we need our trials to be independent. So this is hard, we talked about independence already, right? This was the idea that the conditional probability and the unconditional probability are the same. So we're thinking about something like if I flip a coin and I get 4 heads in a row, what's the probability I get a tails on the 5th coin? Still 0.5, right? The previous outcomes don't influence future runnings of this experiment. Yeah.
So if you thought about this in like a sports game, would it still be this, or is it because it's not necessarily the same?
You're thinking about a sports game like a win-loss?
Yeah.
Yeah, a sporting event wouldn't work for this unless the same two teams were playing over and over and over and over again on like the same time period, right? Because if not, that probability of underlying success, right? If I look at a team 1 year to the next, quality tends to change, right? And so some years their probability of winning would be different when I'm running that experiment or playing that game than the following year. Yeah, so I think of a sporting example where this would apply. It would be like
If during finals, would it have played
yeah, you think of maybe that, but there's so many. So when we're thinking about these experiments, they really need to be identical. So it's hard to apply this to sporting events because every game, things are different, right? They're playing different days, different times, different opponents. If I want to give you like a one that I've kind of actually, maybe we'll look at some data Friday, I can pull it in, maybe it's kind of interesting. Maybe like if you could look at a kicker kicking from the same yard line with the same point differential, and then look at like over and over, see out of this many times, like let's say he kicks the ball 50 times, what's the probability that he makes, I don't know, 40 of them? Well, you can look at his historical accuracy to assume that the probability he makes a kick from this distance is whatever it was in the past, right? So there are some situations you can apply that, but it's a little bit more difficult. And I'll use some like toy examples, but a lot of what you'll think about this binomial is anytime you're like randomly surveying people. I guess like the blue eyes one is a good example because if I'm just randomly selecting people based off of the overall probability of just, of having blue eyes for one person, I can look over, well, if I select 50 people, what's the likelihood that I see, I don't know, 20 of them have blue eyes, right? So we'll work through some more examples here. I think it'll make a little more sense, but yeah, it is really important that they're identical trials. The other questions before we keep moving here? This is just kind of the setup of the problems we're going to see. So what we're then interested in is, okay, out of this many times that I run the experiment, right, out of n trials, what's the probability I see a certain number of successes? So you can kind of think about the blue eyes example. If it is about 15%, and I'll use some easier numbers, let's say I run this trial 100 times. I randomly select 100 people, right? Well, what's the most likely outcome that I'm going to see for the number of people with blue eyes if the percentage was 50%, or probability of 0.15 for any one person I select to have blue eyes? Over 100 people, I would expect about 15 of them to have blue eyes, right? Now, what did you do there intuitively? And I'm jumping the gun here a little bit, but you're really finding the mean of this binomial variable, right? And it's pretty intuitive. You're just taking the number of trials you have, and what you did in your head is you multiply it by the probability of success on any one trial. Okay. So if I select one person at random, I can't see 0.15 people have blue eyes, right? I'm either going to see 0 or 1, but I can kind of find what the expected number is going to be. So over 100 people, the expected number or the mean would be that 15. Now I know that if I move further away from that mean, so I haven't even showed you how we calculate these probabilities yet. But let's think of, if I have 100 people and I'm selecting them at random, I know that I could see 0 people have blue eyes. I could see 1 person. I could see exactly 2, all the way up to 100. Now, a bunch of these outcomes are going to be more or less likely than others. So we said that kind of the number you would expect to see, or what would be the most likely, have the highest probability, is kind of taking that number of trials, multiplying it by the probability of success on any one trial, right? Or jumping the gun once again, but this is really what you were doing in your head. You took 100, there's the number of trials, you multiply it by that probability of success of 0.15. You know that out of 100 people, the most common number of successes, or the people that you see have blue eyes, is 15, right? So what has to be true about the probability that you see 16 people? It's going to be a little bit less likely than seeing 15. Right? Now, once I get out to 100, what's the probability that all 100 people I've selected have blue eyes? Pretty much 0, right? So I don't know, there's like a 0.000001 probably, and it goes out to some decimal. But as I move further from that expected value, my probabilities will decline. And what's the probability I see 0 out of the 100 have blue eyes? It probably isn't quite as low as the probability I see 100 people, but you know, my guess is it's going to be pretty small, right? So it doesn't matter what direction I move in from this kind of expected value, I'm going to see those probabilities decline. Does that make sense? And I'm graphing these, like, how am I coming up with these probabilities? That's the next thing we're going to talk about, okay? So how do I find the different probabilities of seeing different numbers of successes out of n trials, okay? So I'll show this to you, right? It's pretty nasty, right? We'll talk through it. It's really not as bad as it maybe looks on its front. So one thing that we'll have to do is we'll break these down to the pieces. There's something I'll have to make sure that you can all find in your calculator prior to next Friday before the exam. You want to make sure you can find that, because we're not going to use it for the binomial, but we'll use it for the Poisson distribution as well, which is what we'll talk about Friday.
We're testing next Friday, not this Friday.
No, next Friday. Yeah. So like I said, we'll do binomial today, finish it, do Poisson on Friday, continuous distribution on Monday, review on Wednesday, exam next Friday. Okay. So X is just going to be we're looking for the probability that out of a certain number of trials, this random variable X is equal to a certain number of successes. So out of 100 trials, what's the probability X is equal to? 15 successes, right? 15 of the 100 people having blue eyes. Or what's the probability we see? 100, right? There, X would be my 100 value. So X is just the number of successes we're interested in finding the probability of. N is going to be our number of trials, and P is going to be the probability of success on any one trial. These are three things that are kind of given to us, or that we have to have before we even, tackle, we're looking at a specific problem. These are going to be three things that are given to us. Okay. Once we have those, I mean, this part's not too bad, right? Plug in your probability, plug in your number of trials, plug in your number of successes you're interested in. Hopefully, you can do some subtraction, you can raise things to different powers, multiply them by each other, right? The real hard part of this function is that fraction, right? So what's going on there? So for those of you, I don't know, I have an idea when I ask the responses, but so some of you may know this, some of you may not. What's that exclamation point mean in math? You seen that pop up in any of your classes or no? Some people are nodding. Do you remember what it means?
I don't know what it's called, but it's like times it's like getting smaller.
Yeah, so if I have 10 factorial, that's what we call it. That's all right. So if I have this factorial show up, whatever is in front of it, I start with that value and I basically multiply down to 1. Okay. So you can imagine, like, these numbers become pretty big pretty quick. 10 times 9 is 90, times 8 times 7 times 6, right? These are going to become pretty big pretty quick. And then I've got, more factorials kind of down here in the denominator. The proof of why this will give you the probability is hard to understand. We're not going to waste any time on it. For us, we're just going to know that this formula is the functional form for our probability mass function, right? I told you before when we were looking at those other examples, like our probability mass function was like what was in the table. It didn't follow any functional form. Here, our probabilities will follow this functional form. Okay. So there's other ways of kind of showing this, that you're really taking n times n minus 1 and then minus 2. But an easier way to think about it is start with the number that's in front of factorial, multiply all the way down to 1. Okay. So a weird thing about the only other thing that we really need to address before we start looking at some actual examples is that 0 factorial is a weird one because we don't want to be dividing by zeros. We can't do that. It gives us, screws things up. We got to start talking about limits. What 0 factorial is going to be is just 1 for us. Okay. So that's the only other thing that we really need. We could then look at an example like, what's the probability if I flip a coin, and let's say this coin is not a regular coin, right? Is that what I said? Yeah, so it's weighted, so the probability it comes up heads is only 0.4. So if I flip a coin 10 times, what's the probability that 4 of those coin flips come up heads? Okay. Now, if I'm thinking about this, 4 is going to be a fairly likely outcome, right? Because it's the expected value, right? We said before, I already erased it. So the mean of a binomial variable is just the number of trials times the probability of success in any one trial. So 10 times 0.4 here gives us the outcome of 4. But how likely is it, right? What's the probability? So we'll go through, right? Actually, let me see if I have the general form. So identify the 3 things that we were given, which is that we've got 10 trials of flipping the coin 10 times. The probability of success in any one trial is 0.4, right? 40% chance it comes up heads. And then we want the probability of seeing exactly 4 of these 10 come up heads. So here's the general form of the equation. We're going to plug in everything here. And then it's just a matter of getting this entered into our calculator. So if you have like TI 83s and 4s, I believe it's second math. And then you go over to prob or PRB, probability, that's what it stands for. And then that's where you can find that factorial. You got like a smaller calculator. A lot of the times it's going to be under some PRB or some math kind of button you'll see. You might have to hit second and then another button. So it might be kind of, written above it a little bit. Or you can do it by hand, right? So I generally the examples that I'm going to be giving you on the exam are things that you should be able to do by hand. You shouldn't need the factorial button as long as you know what a factorial is. I'm not going to give you something where you have to type in like 20 times 19 times 18 all the way down to 1. But I could give you something like 20 factorial. Right? So I'll show you why, even if I give you some larger values, we can actually break this down and do this by hand, even if we can't find that factorial button on our calculator. And if you are having any issues finding it, what I would first suggest is Google the type of calculator you have. I don't have them all memorized, every single kind of calculator where it's going to be. Google your calculator factorial button. It'll probably be able to find how to find it. If you aren't able to find it, come up and talk to me. I can probably help you after class or something like that. So here, I can write this out, plugging in all my values, right? 0.4, everywhere I see that probability success P, 10, everywhere I see the number of trials, and then 4, everywhere I see X with the number of successes. But why try to enter this into my calculator? I've got a bunch of parentheses that don't really need. Hopefully in our head, I could do, first of all, break this down. 10 minus 4 is what? Hopefully we can do that in our head, right? 10 minus 4 is 6, right? And then 1 minus 0.3, sorry, 0.3. 1 minus 0.4 is 0.6, and then 10 minus 4 is 6. So don't, write this out in the context of your example, plug in your values, but when you go to actually use your calculator, why keep all these additional parentheses? Do the math you can do in your head, make this a little bit easier on you. Then what I generally tell people, if you're having difficulty reproducing some of these answers, break this down into 3 components, right? And you could break this down into 1 if you want, but it kind of prevents you from making order of operations errors in your calculator. So find whatever 0.4 the 4th is, write that down, 0.6 the 6th, write that down, then find this. Now you just have to multiply those, right? It kind of prevents you from accidentally taking this times 0.4 and then raising it to the 4th power, right? Now, if you're comfortable with your calculator using, parentheses around these things to make sure the order of operations are working correctly, that's okay. But I just, from experience, have found that sometimes it's easier for people to break this down into different components. Does that make sense what I'm getting at there? Yeah, okay. So how can we make this a little bit easier? Instead of typing in 10 factorial divided by 4 factorial, even if I can find that factorial button in my calculator, let's think about what this is. So that 10 factorial, I'm just going to write this out so I can really make the point here. 10 multiplied all the way down to 1. What's 4 factorial? 4 times 3 times 2 times 1. Times 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. Well, notice, how can I make this a lot easier to enter into my calculator? Oh.
I was just gonna say, can't you cross 6, 5, 4, 3, 2, 1?
Exactly. Yep, right. Everything here is going to cancel. Now, I don't have to write this out every single time. I know that, if I take that highest factorial, right, n is always going to be greater than 6 or x, right? Greater than 6, greater than x, right? I mean, it could be that x and n are the same value, which I'll show you in a second why that would be pretty uninteresting, or it actually makes our equation quite a bit easier. But now all I have is this to enter into my calculator. And I can think of an even more extreme example. What if I had something that had a pretty low probability of occurring, but I was interested in what's the probability that 2 out of 100 come up had? So there, my n would be 100. So what, n minus x would be 98. Well, geez, has anyone found the factorial button? If you type in 100 factorial, what happens? Hopefully I'm not wrong. These calculators keep getting more powerful, but does it get mad at you?
Yeah.
Yeah, right. It actually can't store that value. It's way too large. So this is actually a really good time to point out sometimes the technology we have has its limitations where it says, you type in 100 factorial. Well, I need a computer to do that. My calculator can't handle it. Well, no. Let's use our brain a little bit. We can actually figure this out because if I start writing this out, what I quickly see is, so 2 factorial is 2 times 1, 98 times 97, all the way down to 1. I mean, notice everything from 98 down here is going to cancel. I can definitely get my calculator to find that value for me. All right, so this is one of those things where if you're using the black box or you're using this built-in factorial in your calculator, yeah, you can't type this in and get it to work. All right. So we just know what those factorials mean. We can see a lot of things are going to cancel, and we can actually solve this pretty easily. Any questions on that before we keep moving here? All right. So I think, let me see what my next example is, and I might hold off. We'll do this one. And then we'll I have one thing I want to do at the end, and then we'll kind of finish the binomial at the beginning of next class. So let's say instead, I know that in the entire population, 30% of adults have a college degree or a bachelor's degree. So I know if I select 5 of them at random, what's the probability that exactly 3 of them have college degrees? Okay. So here, I've got 3 things I always need to identify. What's my number of trials, N? What's my probability of success in any one trial? And what's the probability, what are the number of outcomes I'm interested in finding the probability of? Okay. So here, what would my number of trials be? Yeah, I'm selecting 5 people at random. It's kind of like my eye color example. What's the probability of success that any one person has a college degree? 0.3. And then I'm interested in finding the probability of exactly 3 people having a college degree. So if I go back to this general form of the equation, I'm just going to start plugging my values in. 5 factorial divided by x, or 3 factorial times n minus x. Once again, once I'm going to my calculator, hopefully I can just write this down as 2, right? Make my life a little bit easier. Times the probability of success of 0.3 to the x for the number of successes I'm interested in finding the probability of, times 1 minus that probability of success to the n minus x. Okay. Now, like I said before, simplify these values before you go to your calculator, but then it's just a matter of getting it entered into your calculator correctly.
And then test are again? No, I've always wondered.
No, so should be good question. And I think I originally had this just up on the files, but now if you go to the practice materials, you'll have this formula sheet if it loads. All right, so here's the binomial guy down here. Yep. Yeah, I wouldn't expect you to memorize those. That'd be pretty mean. Right? I may not be the nicest person, but I'm not the meanest person either. So you'll have those formulas, right? So we've got everything written out in the context of our example. Right now, it's a matter of doing plug into our calculator. So I want to show you one thing with this example, and we'll kind of the next class we'll talk about more about this idea of the mean is the most likely outcome and the probabilities fall in either direction. But I wanted to show you one thing here. Let's say I wanted to know what's the probability all 5 of these people have a college degree. Something weird's going to happen, all right? So if I've got all 5, then my x value is also 5. Notice, what does this formula actually simplify down to? Well, 5 minus 5 is 0. Anything to the 0 power is just what? Anybody know that? Anything to the 0 power is just 1. So if I'm multiplying by 1, I can essentially ignore that, right? Multiplying by 1 doesn't change it. 5, so 5 minus 5 is 0. We said 0 factorial is 1. So dividing by 1, we can ignore that. 5 factorial divided by 5 factorial, anything divided by itself, 1, we can ignore that. And all we're left with is take the probability of success and then multiply it by itself, however many trials you're running, or raise it to the power of the number of trials. So why does that work? Okay. Well, remember, what did we say about independent events? If I wanted the intersection of 2 events, one way we could check for independence, we said, was if they're independent, the intersection is just the probability of each event multiplied by each other. So really what we're doing here with a binomial, if I want to know if all 5 people have a college degree, I'm really saying, what's the probability the first person has a degree? and the second person that asked has a degree, and the third person that asks has a degree, and the fourth, all the way to the fifth one. So all we'd really be saying there is, what's the probability the first person has a degree? 0.3 times the probability the second person has a degree, third person, fourth person, fifth person. Another way of writing this is just 0.3 to the fifth, right? So when we want to know all successes or all failures. I didn't do the all failures one here, but that simplifies down similarly. All I'm going to have to do is take that underlying probability of success and raise it to some power. So I have this at the very end, and I moved things around before class because I wanted to know where this was at. And we've kind of already talked about this. But, if I have a long run of tails when I'm flipping a coin, the probability that I see a heads in the next coin flip, it doesn't change, right? It's always going to be 0.5. So at one point, I thought this was interesting. Now it's probably just showing off it. I know how to rank and generate 10,000 kind of coin flips in Excel, and you can kind of see it doesn't matter. Every time I look after there was a head, only one heads in a row, the probability I saw tails on the next flip was about 0.5. Every time I saw two tails in a row, the probability I saw heads on the next flip was about 0.5. Every time in the data I saw three tails in a row, the probability the next coin flip was a head and still 0.5, right? It doesn't matter the previous outcomes. These were independent events, right? As long as Excel's random number generator, it is independent. And that kind of reflects if I'm flipping this in practice, like unless I'm like developing the skill of flipping a coin, excuse me, the probability of getting a head is always 0.5. So I have this old example. It's pretty interesting. So if you go back, what was it, 1913? A roulette table. Hopefully, you guys aren't super familiar with gambling. It's a bad habit. Don't download DraftKings on your phone. But it's a little bit different because you got the green space, but you can kind of think about what's the probability I see either black or red on the roulette table is really about 0.5, right? Every spin should be independent. Okay? So this basically is really rare instance. They were spinning this roulette table. Who knows, maybe there was a mechanical error with it, but it came up black 26 times in a row. So how would I find the probability that this happened? If every spin was independent from each other, the probability that I saw black on the first coin flip would have been 0.5 times the probability of black in the second, 0.5. This would actually be 0.5 to the 26th, right? So we'll look and see what that is in a second. It's basically zero. Like there's almost no chance that this actually occurred, but it did. And so after like, I don't know, 8 or 9 times of this coming up black, what do you think people probably started to do? Yeah, so there's this idea that even though the probability of success hasn't changed, people fall victim to what we call the gambler's fallacy, right? That if I know that if I looked over 1 million spins, about 50% would be red and 50% would be black. But in any like small window of spins, all bets are off, right? I could see in 26 spins, it come up black all 26 times. So after about 8 or 9 times of coming up black in a row, people started really betting red. Like everyone was betting red. But then it came up black the 10th time. And then everyone said, well, it's got to be red. The next one came up black on the 11th spin. So what happened to the casino? They made a shit ton of money, right? So, people falling victim to this gambler fallacy is actually what these casinos like. In fact, I looked a little bit at some of these online sports betting, and a lot of them offer things that look more attractive based on prior results, but those lines they're building are always supposed to be 50% bets. So they're just trying to bait the public into the gambler's fallacy, right? Even though the bet every single time on these websites is 50%, they're trying to get people to buy into it's more likely because it's happened in the past, right? So I don't know, kind of a fun, interesting example. I've got another example. I hope we get to see on Friday. It's kind of fun based on some things we've already talked about. We'll finish up binomial, start the Poisson. Other than that, I'll be posting an online quiz as soon as I get back to my office after my next class around 1. It'll have a couple binomial questions just so you can start to plug in the values, get comfortable, calculate them out, putting them into your calculator. And if you have any questions, then you can kind of ask me next class. Okay. All right. We'll see you guys on Friday.